So at this point, we're ready to handle the third case. And so we had a third case. And remember what we were doing, just as a quick recall. We were looking at the second order differential equation, y double prime plus ay prime plus by equals 0. That led us to look at the equation, which we called the characteristic equation, r squared plus ar plus b equals 0. And then there were three cases. If we had two distinct real solutions, then we talked about what to do there. If we had one real solution, so in other words, one solution of multiplicity 2, we talked about what to do there. And then the final thing that we need to handle is if we have two complex solutions. And one thing that's going to be evident here, and I want to just explain this for just a second, the way that you get complex solutions is from the quadratic equation. So the quadratic equation says, I'm not going to write it because I've already used a and b differently than most people do with the quadratic equation. But the quadratic equation says you're going to get minus this linear term, whatever, plus or minus the square root of some quantity over 2, in this case 2 times 1 is just 2. So you end up with negative something plus or minus the square root of something all over 2. The way that complex numbers get introduced into this equation is if the thing that you're taking the square root of is negative. And it turns out that if it's negative, what's going to happen is you're going to end up with a plus or a minus this imaginary number times whatever the square root is. So the point is that if you get complex numbers, they always come in pairs. So if you were to have two complex numbers that are solutions, what would happen is you would have something like R1 plus or minus I times R2. Those would be your two complex solutions, and they have to come in pairs. These are called conjugate pairs. It's kind of like the conjugate in algebra. When you have square roots, you just replace the sign in the middle. So if you have a complex number x plus iy, then so if this is some number z, then the complex conjugate is x minus iy. So these always come in conjugate pairs. Okay, so that turns out to be just a fact about solving these polynomial equations, is that when you have real coefficients, complex solutions always come in pairs. Now, what this means for us is, let's just copy what happened if we, because it seems like we have two distinct solutions here, and that's going to be very much like the first case. When we had two distinct real solutions, we just have two distinct complex solutions. It turns out that the general solution is going to be y equals c1 e to the, let's call it r1 plus I r2 x plus c2 e to the r1 minus I r2 x. Okay, so that's going to be what our solution is going to look like. And that's just really copying what happened before. Now, one thing that you can do is you can factor out an e to the rx from these exponentials. We know how exponentials work. Turns out complex exponentials work the same way. So we get c1 e to the r1x e to the I r2x plus c2 e to the r1x e to the minus I r2x. And so this e to the r1x is present in both of these. And so what we do is you can factor out the e to the r1x right away. And then you're left with c1 e to the I r2x plus c2 e to the negative I r2x. And so what's left to do is to think about what happens to these quantities. And let's think about what happens now. So we're not quite ready. I haven't quite written the general solution yet. So you can either save a little space or we'll just rewrite it at the end probably. So if we look at c1 e to the I r2x, let's write out what that is. So c1 e to the I r2x is going to be c1 times the quantity cosine of r2x plus I sine of r2x based on Euler's identity. And likewise, c2 e to the minus r2x is going to be c2 times cosine of negative r2x plus I sine of r2x. Okay, and minus r2x. So one thing that's going to be crucial here is that we know that cosine is an even function and sine is an odd function. And so what that means for us is that this is going to be cosine of r2x minus I sine of R2x, because the minus inside the cosine can just get absorbed. It's an even function. And the minus and the sine can actually come out because it's an odd function. And then what we're doing is, if we look at this combination of these two, if we look at C1 e to the I R2x plus C2 e to the negative I R2x, and we add these together, and then we're almost done with this. But if we add these together, C1 e to the I R2x plus C2 e to the negative I R2x, that's going to be equal to C1 cosine of R2x plus I times C1 sine of R2x plus C2 cosine of R2x minus I C2 sine of R2x. And so what you can do if you want is you can just call this C3 cosine of R2x plus C4 sine of R2x. And what I've done here is I've taken and grouped the two cosine terms together. So clearly we can add those together, and then C3 is the sum of those two. But remember, these are just generic constants. And then similarly for the last one, you can take the sine terms and add them together. And then C4 is just going to be the sum of these constants. The fact that those are complex numbers doesn't change anything. They're still just generic constants that we can add together. So C4 and C3 in general are really complex constants, but we don't have to think about that. Finally, here's the punchline. So here's the punchline. If R squared plus ARB equals 0 has two solutions. So if it has, come on, pen. If it has the solutions, which we called R1 plus or minus I R2, then the differential equation is going to look like the general solution to the differential equation is going to be, let's see, y is, let's think about what happened here. I need to go back and look just to show you what all the pieces look like. We have e to the R1x. So we're going to have e to the R1x times the quantity. So times this quantity C1 e to the IR2x plus C2 e to the negative IR2x, which shakes out to C3 cosine of R2x plus C4 sine of R2x. And that's what the general solution is going to look like. So for example, let's do one. Let's say we want to look at the differential equation y double prime plus 9y prime plus, plus 6y prime. Come on, pen. Technical difficulties. Plus 6y prime plus 10y equals 0. Then what's going to happen is you're going to have to look at the equation r squared plus 10r, r squared plus 6r plus 10 equals 0. And it turns out that the quickest way to do this is to complete the square. So this is going to be r plus 3 squared equals -1. So what you want to do is you want your coefficient, your constant term, here to be half of your linear term squared. So remember that the reason why this works is that if you were to square a function, you would end up with x squared plus 2ax plus a squared. And the relationship between these two constants is that if you were to take half of the linear term and square it, you get a squared. So here we take half of the linear term, which is 3r, square it, you get 9. So I want this to be 9. So I'm going to move 1 over. So I'll subtract 1 from both sides. In fact, let me write this for the first one. So we're looking at r squared plus 6r plus 9 equals -1. And then this left side, is the reason why we did that is that we can write the left side as a square. This is r plus 3 quantity squared. That's going to be equal to -1. And that tells you that r plus 3 is going to be plus or minus the square root of -1. In other words, r plus 3 is going to be plus or minus I. And then finally, this tells you that r is going to be -3 plus or minus I. And therefore, the general solution to the differential equation is going to be e to the -3x times c1 cosine of, this is 1i, so this is going to be cosine of 1x plus c2 sine of 1x. If, let's do just one more. Let's look at y double prime. So let's make it an interesting one. Let's look at y double prime minus 4y prime plus 29y equals 0. And that's going to lead us to look at the equation r squared minus 4r plus 29 equals 0. And it turns out that this is going to have solutions. You can check this. This is going to be 2 plus or minus 5i. And therefore, the general solution to our differential equation is going to be e to the 2x times c1 cosine of 5x plus c2 sine of 5x. And with that, we can handle all three cases for linear homogeneous ODEs with constant coefficients. So we are completely done with those. In the next video, we'll do just a handful of examples where we talk about how to put everything together, but we've handled all of the theory behind those.